Welcome to Project 22048. Our project is titled CytoMech, a microfluidic system for determination of platelet stiffness. We are sponsored by Dr. Slepian and the Arizona Center for Accelerated Biomedical Innovation. The team is made up of Jacob, Anaya, myself, Talia, Kellen, and Michael.
Over 900,000 people are affected by venous thromboembolism each year. A key component in VTE are platelets. Little is understood as to the physical response that a platelet has to mechanical stimuli. In an attempt to further the understanding of the physical response a platelet has to this stimuli, we developed a laboratory setup that is able to measure the elastic modulus of a single platelet. What this team has been tasked to do is to condense the setup into a marketable design.
Our project utilizes ideas from one of Dr. Slepian's past research papers, which involves using dielectrophoresis, or DEP, to deform platelets as the applied shear stress increases. And to perform DEP, there's a lot of bulky electronical components that are involved. So we have the oscilloscope, function generator, and the amplifier. And for our project, we took all of this and made it into a more compact electrical system right here. And our project will continue to utilize fluorescence imaging. So right here we have this really big, large, expensive camera, and then we redesigned the entire fluorescence optical system to fit inside this small, compact space right here.
This is our CytoMech system. As mentioned before, the purpose of this design is to make the CytoMech easier to use and easier to transport, as well as greatly reduce the cost of the CytoMech. I will be giving a brief overview of our 5 subsystems, which include our electrical subsystem, our microfluidic chip subsystem, our software subsystem, and mechanical subsystem, as well as our optical subsystem.
As shown here in our system body diagram, these 5 subsystems all simultaneously work together, completing various functions. Our chip is designed to trap and deform platelets via DEP. Our optical system will show platelets at a magnified level, and we will be able to view the platelets using fluorescence. Our electrical system, which will allow the user to supply 0 to 100 volts peak to peak to the chip in order to conduct DEP. Another subsystem is our software assembly, which works with the optical system to analyze image data to determine deformation. Using that data alongside voltage measurements, we are able to obtain the stiffness, which sends data from the backend to a GUI for the user. Lastly, we have our mechanical system that houses our entire system. We will go into more detail on each subsystem and its testing. Our chips must be designed to trap and deform platelets via DEP and be capable of sustaining 100 volts peak to peak with minimal wear. Next, our chips must have a 10 micron channel to enable flow of platelets throughout the chip. And lastly, it must be biocompatible. The microfluidic chips are used to trap platelets with a design printed on the slide made using photolithography. This design will allow us to place the platelet within a 10 micron channel in order for the electrical system to deform the platelets. We create this chip through our fabrication process, where we first clean the slides and apply an HMDS layer for the photoresist layer in order to prepare for the mask aligner, which exposes our optimal design on the slide. In preparation for the final steps before use, we measure the surface depth of our chip in order to ensure the slide is designed correctly. We then conduct metal deposition with 3 layers of metal, which are titanium, gold, titanium. These metals are used for their tensile strength and biocompatibility. Lastly, we conduct liftoff using dimethyl sulfoxide, or DMSO for short, in order to remove excess metal material, leaving us with the design needed for DEP.
The following are requirements met by our optical system. Our optical system is able to show platelets magnified at 100 times. It is able to reflect blue and white LED light onto the platelets. And the optical system is able to transmit input image data to a smartphone camera, then into the software system backend. Our optical system includes a custom fluorescence microscope. On this device, we have a source LED that shines blue light and reflects it off this dichroic mirror, which passes down into our sample, fluoresces the dye that's labeled on our sample, and then white light passes up through the sample, through the dichroic mirror, which is semi-permeable to white light, and into our camera, which processes that information.
The CytoMech electrical system had to satisfy several simple requirements in order to accomplish our goals. First, it had to create a low voltage sine wave at a frequency of 1 megahertz. It then had to amplify that sine wave to a range specified by the user from 0 to 100 volts peak to peak. It had to support control via USB cable. It had to be operable using standard US wall power, and it has to be isolated from the user to ensure safety. The functional idea of the CytoMech electrical system is that it would take a digital input, square wave, convert it to a sine wave, and then amplify that sine wave to a much larger sine wave based on the user's specifications in the digital square wave. Here is an example of what the system looks like, along with each of its components: the amplifier, power supplies, oscillator and smoothing circuit, and the Arduino microcontroller. Together, these form the entirety of the CytoMech electrical system.
The system requirements for the software backend will be: the system will take readings from the optical and electrical systems. The system will process optical data to identify strain data. The system will process electrical data to identify stress data. Stress and strain data will be used to find stiffness data. Stress and strain data will be used to find hysteresis data. And the calculated values will be within 95% accuracy to previous results. To do this, we use image processing to get the image from the optical system into a usable value. And we use the voltage data obtained from the electrical system to find the stress on the platelet at these times. This is then fit. We're using a linear regression to get our stiffness. The data being put on using least squares to find the hysteresis values.
We first load our diluted platelet sample onto the microfluidic chip slide with the fluorescence dye, which we then use a blue LED light to image those platelets between the teeth on our microfluidic chip. And then we increase the voltage by increments of 5, and at each increment we take an image of the platelets to calculate the strain of each platelet at its voltage increment. And at the end, we step down our voltage back to 0 volts.
After completing this project, we've come up with a few things to make our CytoMech system a little bit more robust moving forward. First, we would like to make our electrical system a little bit more compact and also address the fact that our oscillator circuit is sometimes unstable, so we could make it more stable by looking into digital oscillator circuits as an alternative to analog oscillator circuits. As far as our software system goes, we ran into some trouble where platelets might overlap each other and cause difficulty in identifying how much they've actually stretched out in order to compute the stiffness. So moving forward, that's a problem that we can look into solving. And finally, our chips team has come up with ideas to make our microfluidic chips more robust to accommodate higher voltage and even to accommodate different cells beyond just platelets by expanding the channel that the chips occupy.
The biggest lesson our team learned was to seek professional help early on into the process. Our electrical subsystem was aided greatly once we found a technician, although it was sort of late into the project. And with microfluidics, the professional help that we did have in Tucson was helpful, but we could have used more to finish the project faster and more completely.
On behalf of the CytoMech team, we would like to thank our sponsor, Dr. Schleppian, Daniel Palomares, Dr. Hetherington from the ECE department, and Sam Bassett from Apex Microtechnologies for all of their support and help with our verification processes.